So the third talk this evening is by Alex Bronstein of the Technion on geometry learning 3D curve.
Thank you. Thanks for the invitation. And if you missed functional maps, I would like to go back to this topic. So this is basically a few works. This talk is based on a few works joined with this nice gentleman and this nice lady. Just as a brief reminder, we are talking about correspondences between deformable 3D shapes. So basically, we are interested in establishing a map from one manifold to another manifold. For most of our users, these would be two-dimensional manifolds embedded in the three-dimensional Euclidean space. And the problem can be actually formulated very rigorously in geometric terms if we have basically this map between isometric shapes. So then we can, for example, preserve some geometric quantities like distances, for example. We want this map to be intrinsic in the sense that any deformation of the shape will make this map basically will still keep this map invariant. And of course, in real life situations, even though these are very high quality data, but even in this case, the shape here is non-isometric. It's a different person. It has a very different geometry. So even formulating this correspondence problem in geometric terms is not a trivial task. And what Emanuele discussed 3 days ago, basically how to deal with partiality. This is of course partiality and clutter. This is of course a even more challenging problem. So I will briefly remind you the computational pipeline that is based on functional representations of correspondence. And basically we have heard from Max and from Nir and from Emanuele about different approaches to this pipeline. There were 2 points that were left unaddressed, or at least I believe not sufficiently addressed. So I would try to give some answers, or probably I will have more questions than answers, but at least I will try to address these 2 points. So basically, the trivial way of thinking about correspondences between shapes is by modeling the correspondence as a map between 2 manifolds. But this object is very difficult to work with. It's difficult to, for example, solve an optimization problem. It's not even clear how to represent such an object. But basically, the very elegant idea that was proposed by Max Ovsyannikov and his co-authors in 2012 was basically to lift the problem into a much more complex space, basically a space of real valued functions on manifolds, and then basically encode the correspondence as a map between functions, between spaces of functions. So basically by trivial laws of compositions of functions, basically this map can be shown to be linear. So basically, instead of working with maps between complicated domains, we have linear maps between even more complicated spaces. So basically, if we have a function f, I don't know if I have a laser pointer here. Yeah. So if we have a function f on some manifold x, I will have this linear operator t that will produce a corresponding function on another manifold y. Okay, so if I feed this operator with functions, I will create corresponding functions on the other shape. So now, if I equip these 2 manifolds with orthonormal bases, I can decompose this function f and this function g into a Fourier series with respect to these bases, and of course I can truncate this series to get some kind of band-limited approximation. So now, once I change the basis, this linear operator can be encoded by a k by k matrix, where k is the number of basis functions that I'm keeping for my approximation. So now, if I'm given a function f and a knowingly corresponding function g that is related by this correspondence operator, I can rewrite this relation with respect to this pair of bases as a linear equation between the Fourier coefficients a and b related by this matrix C. And the matrix C is just just basically every ijth element of this matrix is the inner product of the basis function phi with the basis function psi composed with the correspondence. And of course the correspondence is unknown and it is encoded in the structure of this matrix. So basically if now I'm now given these are the Fourier coefficients of some set of knowingly corresponding functions fj and gj. So these are their corresponding Fourier coefficients. This is my matrix C that relates between them. So if I can construct such such corresponding functions, basically with which I'm probing my correspondence, basically the problem of finding the correspondence simply boils down to solving a linear system of equations. So if I do this least square solution, I get the matrix C that encodes the correspondence. Okay, so this was the main idea of the original paper. The problem is basically where do I get these corresponding functions? And one of the standard approaches is to use descriptors. So basically, I will assign some vector valued function to every point on the manifold, and it will be constructed in such a way that it will be sufficiently repeatable, sufficiently stable under a certain class of deformations, let's say. So if I have, for example, this shape and some deformation of this shape, I will see more or less the same descriptor field on both. Okay, so then basically the dimensions of this descriptor can be thought of as corresponding functions. So if I have some multidimensional vector value descriptor, basically I can think of every dimension as a probe function. Okay, so and if I do this construction well, I can hope to extract correspondence from this descriptor field. Okay, so basically this is a necessary ingredient to this problem, and basically what we have seen so far didn't. So we use some kind of ad hoc construction. So I would like to try addressing this problem in slightly better way by proposing something that is optimal. I'm not particularly proud of this because I'm using deep learning, and this is not something I understand. So basically, everything that I will show here can be done better, and I can actually discuss what can be done better. But I think what is interesting is the loss function that I'm going to use. Okay. So basically, let's see how we can learn descriptors for a specific task. Basically, suppose we have a collection of shapes with known correspondences marked, basically labeled as ground truth, and basically I would like to learn descriptors. I would like to learn descriptors in the best way. And this is a very common problem that computer vision people have been solving in the past, I would say 15 years at least. So one of the standard approaches is to take some vector in the input that contains sufficient information about, let's say, the geometry of some surrounding of a point. So this would be a point-wise descriptor. And one of the off-the-shelf solutions that works really well is this so-called shot descriptor that is simply a histogram of normal orientations in some vicinity of a point. Again, there is nothing good about it except that it works well. So then I will do a nonlinear transformation of this descriptor by basically a neural network, and here any sufficiently rich nonlinear transformation will work, some parametric transformation. As a result, I will get a new descriptor that hopefully is better. Okay, so now I will take two descriptors, basically 2 points, one on shape x, another one on shape y, that I know correspond. Basically, I know from my ground truth labeling that they correspond, and I would like the descriptors that come from corresponding points to be mapped ideally to the same point or somewhere nearby with respect to some metric, let's say L2 metric. And if I have points that I know that don't correspond, I would like their descriptors to be mapped far away from each other. So basically, this kind of learning scheme is known as the Siamese loss. Basically, I have two instances of the same network, so they share the same parameters, and I would like to learn the parameters such that, let's say, descriptors coming from a positive pair are mapped nearby, so I would like to minimize this Euclidean distance, and descriptors coming from a negative pair, basically to non-corresponding points, they should be mapped at least some margin mu apart. And this is a very standard hinge loss that is used for this purpose. So again, this is something that is very common in metric learning, in machine learning and computer vision literature. If we do this to our problem, basically, and I count the number of correctly found descriptors as function of the number of best matches, so I sort my descriptors by the distance, and basically I count how many of them hit the correct correspondence in the ground truth. So you can see that there is a big improvement compared to the original input descriptor, to the raw input that I was using. Basically, there is a gap of probably something like at least 20% here. However, this kind of a loss function completely ignores the geometry of the problem. Basically, I might have the first match coming from one point, let's say here, and the second match can come from a point here. It could be still a good descriptor, but basically there is nothing that, for example, promotes continuity of my map. And if I indeed try to evaluate the quality of these descriptors by seeing how many correspondences are mapped correctly within a certain error tolerance on the manifold, let's say in the sense of geodesic error, the improvement is not very great. And again, because I'm not taking into account any geometry of the problem. So basically, what I would like to propose is a slightly more complicated scheme. Basically, I know that I'm going to use the functional correspondence pipeline. So I know that I'm going to use my descriptors. I will project them onto some truncated eigenbasis of the Laplacian on both manifolds. Then I will solve this least squares problem, and this will represent my correspondence. So let's incorporate this knowledge into the loss function, which I'm using to train the descriptors. So it looks slightly more complicated, and I still have this Siamese type of network. Basically, I have two instances of the same neural network that share the same parameters. Then I do the projection of the output descriptors on my basis functions, phi and psi, on the two manifolds. This gives me the Fourier coefficients. Then I solve this linear system of equations in the least squares sense. This is basically the functional map layer that I'm adding. And basically, if I now think of this correspondence C, I can recreate it back in the spatial domain, in the primal domain. So basically, I can recreate this matrix by multiplying it by phi transpose from the right and psi from the left. I have an n by n matrix. And if I normalize, so basically, if I normalize the columns of this matrix, so it might have negative values. So I have to take absolute value. If I normalize the columns, I can think of it as the probability distribution of a point on the shape x to be mapped to some point on the shape y. So basically, there will be some. It will look like something blurred because I'm just keeping the k lowest frequencies. But basically, with respect to this distribution, I can compute some moment and use this as a loss function in my learning problem. So basically, I can, for example, compute this second order moment using the geodesic distance on the shape y. So basically, it will be the second order moment around some ground truth point that I know the point x has to be in correspondence with, and basically, the closer I'm to this point with respect to this moment, the better I'm in terms of this loss. So the spread, the variance of this probability density function is the result of the truncation. However, the bias can be decreased by the learning, and this is exactly what this learning scheme tries to do. So basically, if I minimize this loss function now, I don't get such a spectacular improvement on this CMC curve, but I have a quite significant improvement on a criterion that takes the geometry of the problem into account. So basically, it improves a lot. And again, everything here can be done better. I think it's nicer to do this neural network in a completely intrinsic way, maybe starting also with some intrinsic descriptors. But I think what is important is the loss function. Basically, it has to incorporate the knowledge of the specific task that we are aiming these descriptors for. And I will show you more results from these kind of descriptors that we call FMNet, functional map neural networks. I will show it to you at the end, basically combined with another technique that I would like to describe now. So basically, this was on the descriptor part. So it's a way to learn task-specific optimal descriptors. But still, once we compute this matrix C, we compute the functional representation of the correspondence. We have think of it if we, for example, think of this matrix as a pointwise representation of the map. It is still some blurred version, right? Because we threw the high frequencies. So we need somehow to reconstruct the pointwise map. And basically, this is something that disturbed me for many years, and it still disturbs me. If we try to construct the pointwise map from this representation, the result is never satisfactory. We cannot even guarantee smoothness or surjectivity of the result. So, for example, these are the outcomes of two common ways to recover pointwise maps. This is using ICP. This is using CPD. Coherent point drift, basically doing rigid or non-rigid alignment in the spectral domain. So basically, what is shown here, these textures should be transferred perfectly here, from this shape to these shapes. It's a correspondence computed from this left-hand side shape to these two shapes, and the green regions here are points that have no preimage. So basically, the map is not surjective. These points are not corresponding to anything on this manifold. Okay, so in many applications, for example, in computer graphics, this is not a satisfactory solution. We would like, ideally, to have a bijection, something continuous, something maybe smooth, right? And basically, the standard techniques that people are using are not satisfactory from this perspective. So I would like to try addressing this problem. And I'm not claiming that I have a perfect solution, but I think I have a better solution. So let's have a slightly different look at the correspondence problem. Well, because it's difficult to visualize something four-dimensional, let me start with a two-dimensional visualization. So I will take one-dimensional shapes, which are basically contours. So this is shape X, this is shape Y. And I can think of correspondence between these shapes as a two-dimensional, as a one-dimensional submanifold in a two-dimensional product manifold X cross Y. Okay, so in this case, the product space can be thought of as a torus, because these are two closed curves, and the correspondence here, this pi, will be this nice smooth curve on the torus. Okay, and this is actually quite an old result. It can be shown that any diffeomorphism from X to Y basically can be represented as its graph surface, basically this submanifold pi, which is differentiable connected closed surface or curve in this case in the product space. And the other direction is also true. Basically, any such submanifold represents a diffeomorphism between X and Y. And basically, we can formulate the correspondence problem as minimization of some energy of the submanifold over all submanifolds in the product space. And there are many, basically, or a few works in the past that attempted solving this problem in this way, but I think all of them suffer from extremely high computational complexity. Okay, so allow me, instead of drawing the torus, allow me to parameterize the torus on the unit square. So just remember that we have circular boundary conditions here. So this would be my correspondence. So suppose that I'm given some input correspondence. So basically, I would like to think of my correspondence problem. Suppose somebody gives me an input correspondence. It might be partial, it might be noisy, it might be given as a distribution, something that I'm getting, for example, from functional maps. And my goal is to denoise it. So basically, I think of of this manifold pi as an image in the product space. So now, using this analogy, I can think of denoising correspondence, or basically doing inference of the correspondence from this noisy input. So let's just have a very simple example. I have these two curves, and I'm given as the input the perfect correspondence between them, which is encoded by this identity matrix in the product space, except for 2 points, xi and xj, which are flipped. So this is noise in the input. These are 2 outliers in the input. So what I'm going to do is the following scheme. I will first do diffusion on x. So diffusion on x will correspond to blur in this horizontal direction. Then I will do diffusion on y, which will correspond to blur on in this vertical direction. Okay? And this scheme was proposed previously by Ronen Talmon, for example, and Rui Lederman. Basically, doing this alternating diffusion, they formulated it as an algebraic problem. But basically, I would like to add another step, which will be crucial for our purpose. I would like then project this result back onto the space of bijection. So basically, I would like now to find bijection that maximizes this density. So this best bijection will completely remove the outliers. Okay, just with one round of blur on x and blur on y. Okay. Another illustration. So suppose I have this one-dimensional. Suppose I have this one-dimensional distribution. So I have 2 peaks at. So I have two peaks at one at 8, another at 20, and they are reversed. So I will do diffusion. This on x. The 2 peaks will be blurred, and now my correspondence, what it will do, it will flip the points at 8 and at 20. The rest will be copied as an identity. Exactly the same situation that I described before. So now I do diffusion on y. These outliers that were created here and here will be completely smoothed out, and the modes of these two distributions will still be as those of the initial peaks. So if I now do the projection and I take the modes, I will still get this correct correspondence. Okay, so basically what this leads to is a very simple algorithm. I will take some initial correspondence. I will denote it as by pi in. So I'm denoting by pi a permutation matrix, but it doesn't necessarily need to be really a permutation matrix. It can be noisy. It can be sparse. Some rows and columns can be completely zero. It can be distribution. It can be something that is not necessarily 0 and 1. So I will first multiply it by diffusion kernel on x from the right, then diffusion kernel on y from the left, and then I will project it onto the space of permutations. So I will maximize this inner product with all the permutations, and basically then I will just take the output of this step and iterate it multiple times. I can repeat this process until it converges to some solution. So basically, if we look at these iterations more in details, basically what we see that first of all, if kx and ky are positive definite matrices, this objective function is strictly convex on the Birkhoff polytope, and basically we can replace this problem with a relaxation on the Birkhoff polytope. Of course, we are trying to maximize, say, convex objective, so we cannot guarantee any global solution, but at least we can guarantee that the relaxed problem will give us an exact permutation matrix. And these iterations, basically, there is a very renowned optimization algorithm called Frank-Wolfe's algorithm for convex functions, and in general the so-called convex-concave procedure for non-convex functions that basically we can recognize our iterative procedure as these iterations. So essentially we are trying to maximize this function that is quadratic in pi. Okay, so we are looking for a permutation that maximizes this quadratic function. So this is this is a quadratic assignment problem. Another way to write it is basically by replacing this inner product with an L2 norm. Because basically, I'm trying to permute the rows of one kernel and the columns of another kernel in such a way that they match in the best way in the Euclidean sense, or if you prefer, that their correlation is maximized. Okay, and here using kernels, of course, is much better than using distance matrices, for example, because kernels are positive definite and they have this property. So basically, we can think of this as a filtering procedure on some input correspondence. As the input, I can have sparse pointwise correspondence, which would correspond to a binary matrix, which is not exactly a permutation matrix because it has zeros in some of the columns and some of the rows. It might start with some correlation of two descriptors on x and y, and it might be, for example, a functional map. So it will not be a permutation matrix. So after the first step, we do the projection onto the space of permutations. We will get a permutation matrix. Of course, basically, so what we are currently trying to solve is a quadratic assignment problem, right? It's a notoriously hard problem. We are solving it as a sequence of linear assignment problems, basically a sequence of linearizations. The linear assignment problem is still a hard problem. We are solving it by the auction algorithm with a multi-scale acceleration. So I admit that the details of this multi-scale scheme are quite ugly, but still it works in several minutes on meshes with, let's say, 50,000 vertices. So it's surprisingly fast. Okay, so I will just show you some examples, and then I would like to discuss a few alternative interpretations of this procedure. So the input here are 20 sparse corresponding points that are exact. They are taken from the ground truth. Of course, most of the points on the target manifold have no correspondence. So that's why initially everything here is green. So the map is utterly not surjective. And this is the corresponding error in terms of basically the geodesic distance to the nearest corresponding point. Of course, the error here is very big, 7% of the geodesic diameter of the shape. It's huge. After the first iteration, you can see that the error improves, and the texture that is mapped here, we are getting a bijection. So basically, there are no more missing points in the image, and the texture is still quite noisy, but at least the overall layout of the correspondence is captured correctly. A few additional iterations, you can see that the result is much better now. It looks very, very smooth. Just a few zoomed in details, you can see how this noisy texture after a few iterations becomes much better. Another example. Here the input is now a functional correspondence. This is the result of what I'm getting with an ICP algorithm, rigid alignment in the embedding space, and CPD, non-rigid alignment, coherent point drift. So both solutions are non-surjective. This is what happens when we apply this product manifold filter. I think one iteration of the product manifold filter on these inputs. So the result is surjective and the error is much better. So if I now quantify on this trade-off curve between the percentage of correctly found correspondence versus the tolerance radius, so these are the results on the same scape data, basically scanned human shapes. These are the three results obtained by nearest neighbors, bijective nearest neighbors, and coherent point drift, basically recovered from the functional map. And this is what happens when we take these outputs as the input and we do a few iterations of this manifold product manifold filter. So basically, those inputs are improved by this iterative procedure, and basically the gap is quite significant. Another example. So this is again the scape benchmark, scape data of scanned human shapes. now I'm using as the descriptors the optimal descriptors that I showed before, and it actually exhibits a significant gap compared to all other state-of-the-art techniques. This is the same experiment on the Faust benchmark. So what is shown here, there are a few basically competing methods for learning descriptors, basically using different neural networks. Yes?
So in the previous example, was it after the refinement?
Yes, yes. This is the result after the refinement. Yes. Yes.
For each or no? Just for the FML? For each?
I think it's yeah. The result of the refinement is for each. So it's so I simply didn't have space on this plot to show all the basically input. So the inputs were significantly worse without the refinement, and FMNet was actually significantly worse. You can see it here on another data set on Faust. So this was the raw output of FMNet descriptors, which is okay but not great. With refinement, it is basically almost perfect. And it is surprising because we didn't take this quadratic loss into account when training the descriptors. This is, of course, something that has to be done. This is basically a work in progress, but I'm sure it will significantly improve the performance. So there is now a new Faust, a dynamic Faust data set, which is more challenging. So it will be interesting to test it there because this benchmark becomes too simple. And again, you can see that that all these competing techniques, when followed by post-processing by this filter, actually the performance improves significantly. So this dotted line is the raw input, and the solid line is the output of the filtering. I think a few iterations, not more than 4 or 5. Okay, so let me show you maybe with a little bit of hand waving a few alternative interpretations of this iterative procedure. So one of them, let's just remind ourselves, if we are minimizing, I'm writing everything in the discrete setting, but if L is the Laplacian matrix and we minimize something like this, let's say subject to unit norm constraints on F, basically this is the Dirichlet energy of F, and we can write it as the maximization of basically if we take this monotonic function of the Laplacian, we can replace arg minimum with arg maximum, right? And this is nothing but the heat kernel at time t. So what if we now observe our kernel matching energy that we are trying to minimize, this quadratic assignment problem score, sorry, maximize, not minimize. Basically, we can recognize, we can write it if I parse my permutation matrix pi into a long vector. Basically, I can write here a Kronecker product of the two kernel matrices kx and ky, and basically what we have here can be interpreted as, so this product kernel can be interpreted as the heat kernel on the product space as x cross y. This is a trivial, basically, construction of the heat kernel on the product space with a regular direct sum metric. And what we can see here is just the Dirichlet energy in the product space. So we're minimizing some kind of bending energy of this correspondence manifold in the generally non-Euclidean 4-dimensional space where it resides. So in the one-dimensional case, it's easy to show that this procedure will actually minimize the length of the curve. In 2D, probably it would correspond to some area minimization. Another interpretation, we can think of what we are doing as kernel density estimation and then followed by some kind of maximum likelihood procedure. So if this is, again, a 2-dimensional visualization of the product manifold, what we are given, let's say we are given a few sparse noisy points as the input correspondence. What we are doing, we are putting 2-dimensional kernels around each point, and this is an empirical estimate of the density of the correspondence, and then we find the best bijection, basically, that maximizes this density. And if we discretize this continuous setting, it is exactly the energy that we are minimizing, okay, for a single iteration of the filter. So basically, this again, this fitting of a bijection that maximizes the density it can be interpreted as a maximum likelihood, but basically this is our projection onto the space of permutation. It would be interesting here to consider some kind of some more complicated kernel. So here we just have a trivial separable kernel kx times ky. Maybe if we lift this problem into some more interesting space, we can still have a separable kernel in this lifted space that will look like a very complicated kernel in the original space, maybe something that resembles non-local means or bilateral filter in case of images. So if you like this image processing analogy, many powerful techniques can be probably generalized here as well. So just a few examples. So this is the initialization, a few iterations, and we get the correct correspondence. Just remember that we have cyclic boundary conditions here. Okay. Another interpretation. So if I now substitute this permutation matrix in the form of so if I now substitute the kernel matrix in its Fourier representation, so it will be just the negative exponent of the diagonalized Laplacian here and here. I can now group the matrices differently, and I can think of this psi transpose pi phi as the functional representation of the correspondence matrix. Okay, so basically what we are doing is essentially filtering the correspondence, low pass filtering the correspondence matrix from both sides, right, on x and y. And then we are doing conversion to a pointwise map. So we are low pass filtering, basically we are blurring, and then we are converting to a pointwise map, which is sharpening. So we have alternating blurring and sharpening steps in this iterative procedure. And if we just do truncation, just basically multiplying by a rectangular window in the frequency domain, this creates all these ugly oscillations in the space domain, basically Gibbs phenomena. If we are using this Gaussian kernel, just remember that lambda has the meaning of squared frequency on two-dimensional manifold. Basically, we have much cleaner windowing in the space domain. So there are much less oscillations as a result of this windowing. So basically, this low-pass filtering with the heat kernel looks like a good thing to do. I will show you some surprising results that I really find hard time explaining to myself. So here the input are these 2 points, just these 2 points. The shapes are totally non-isometric. You can see they are very different geometrically, and this is the correspondence that we find. So it makes semantically it makes a lot of sense. It is nice. It is smooth. It is surjective. Another example, just 1 point. So this is the correspondence between this shape and this shape. It looks accurate. Of course, if I give you as the input some wrong point, it will still converge to some nice smooth correspondence, but it will be wrong. This is a crazier example. So here I have a one-dimensional manifold that I'm trying to match to a two-dimensional manifold. There is no continuous mapping that exists in this case. There's no way to map them continuously. But still, you find something that looks meaningful. There is a discontinuity, but this discontinuity somehow in all our experiments tends to be shortened, to be minimized. So I will show you another example. So this is a sphere mapped to a torus. I'm starting with random initialization, completely random, and this is the result. And this is consistent. It basically repeats for practically every random initialization. So you can see that this is the discontinuity. We cannot avoid it, but somehow it goes to the inner circle of the torus. So its length is minimized. So I think based on these observations, we can conjecture. We don't have a proof of this yet, but we can conjecture that this procedure minimizes these discontinuities whenever the map has to be discontinuous. Of course, there are some failure cases. So, for example, here, I don't know if you can see it, but the right leg maps to the right leg, but the left arm maps to the right arm. There is an intrinsic symmetry. And there is some point of discontinuity here on the body, on the torso. I don't know if you can see it. Basically, the texture is twisted in some weird way. So basically, this is probably some bad local conversion. But surprisingly, this procedure converges very well. There is a trade-off between taking large variance. So large variance gives very good and very fast convergence. But if you want more accurate result, you need to take a smaller kernel. So if you take a large kernel, so this is one iteration after random initialization. So basically, you can see with the large kernel, it converges to a good correspondence. If we take a small kernel with a small variance, starting with random initialization, it will converge to something like this. It will be trapped in a local minimum. It will be unable to go out of it. So what we are doing in practice, we are doing a few iterations with a large kernel, and then we gradually anneal basically the kernel variance by reducing it over time. So I think this procedure, first of all, it is efficient. We have code. You are welcome to try it. This procedure can be used for other settings as well. First of all, even in the code that I'm sharing, we can easily extend it to the partial setting. We can just add slack variables that have no data term, and basically those will easily handle partial correspondence cases. I think what is annoying is that we start with a discrete bijection problem instead of discretizing the continuous bijection problem, which I think would be a smarter way to go. I think what would be extremely interesting to do here is to actually learn the kernel. So we currently take hit kernels as something granted, and they work very well. But I'm sure if we learn the kernels, it can produce better results. So what we are currently working on, we would like to substitute the exact solver of the linear assignment problem by some iterative procedure which we truncate after, let's say, 5 iterations, and we regard everything as a neural network end-to-end. Basically, plugging into it some parametric representation of the kernel, let's say, as a function of the Laplacian, can be actually used as a basis for learning the kernels. It can give hit kernels or something else, maybe something anisotropic that works well for a specific class of shapes. So I think, just to conclude, I think, first of all, the first part that I showed with learning the descriptors, I think it shows that incorporating geometric structure into the learning problem, in this case into the loss function, can actually be very beneficial. So we had a tiny amount of training data and a very small net. I don't remember how many parameters, but a few thousands, and the training set was very small because, as you can imagine, the 3D data are not as abundantly available as 2D data. So it's basically orders of magnitude less data and less parameters compared to what, let's say, visual object recognition people do all the time. Still with this trivial idea, we can get a significant improvement over state of the art. Then basically going to the second order relations, basically going to pairwise relations, I think it is beneficial to think of correspondence problems as denoising or inpainting or image enhancement problems in the product manifold. I think we are underusing the full potential of what can be done there, because basically many image processing techniques that achieved state-of-the-art results until a few years ago can probably be generalized to this setting as well, and to work to basically do this denoising or inference of the correspondence from some corrupt input. It is surprising that it works well. I don't know, I don't have an answer why. We observe that we use a generic auction algorithm for solving the linear assignment. We observe that the time scale of the hit kernel has a crucial impact on the convergence of the method. So probably the rank of the kernel, or the effective rank of the kernel, has an important impact there. Probably it can be done much better. I'm sure there is at least one order of magnitude in runtime that can be improved there. We are now working on it, and I think it's interesting that there are a few diverse interpretations that can be given to this procedure from completely different perspectives. So somehow I think it basically relates together or brings together different fields, and maybe we can borrow different techniques from these fields to solve correspondence problems. And as I said, the code is available. You're welcome to try it. It's a MATLAB code, but we'll also probably do a Python code very soon when we finish the kernel learning part. So I'll finish here. Thank you very much.
So I remember a talk about the Drosophila, the fruit fly, and in this talk it was explained that between the smell organ of the Drosophila, the nose, and the brain, there is a layer of neurons which kind of generates white noise, a low one normally, but if the smell is very, very weak, the white noise goes up, and then the Drosophila finds the fruits more easily. On the other hand, when I visited a cubicle office with many cubicles, they have loudspeakers which spread out white noise, and it was explained to me this has the effect that you don't understand people which talk far away, but you understand much better people who talk near you, so you can have meaningful discussions in there. And then I think this denoising in the product, or this Gaussian blurring of the functional map, this could be interpreted as going up in the Sobolev space very high. You even go up to this reproducing kernel Hilbert space with the Gaussian, where the Hilbert space consists of entire functions of a very certain type and so on. So perhaps there is an interpretation in what I objected to in this previous talks about the functional map.
So maybe a sequence of projections, right? You refine your space and then you project onto something very
exactly,
very
which
broad.
means you just take the norm in a higher Sobolev space of your finite dimensional.
I see. That's very interesting. Yeah, we haven't thought about it. So a different interpretation that I give to it is basically we can think of what we are doing here as a kind of projected gradient descent step. And what we would like to do is to introduce some inexactness to make it converge faster. So basically, we would like to do some different linear projection and maybe a different nonlinear projection as well to make it converge just in a few iterations. So this is something we are currently trying. So at least there is this theoretical explanation. If it works, then it would be a small surprise.
So regarding the projected gradient descent, it seems it's the same algorithm that was used initially by Facundo Memoli for the Gromov-Wasserstein, and in practice it's true that on the Gromov-Wasserstein, which is a similar problem, we observe that for some shapes it converges to, for some pair of shapes it actually converges to the global minimizer, which I think is more or less also what you observe in your practice. But do you think there is a theory behind it that we could show that for relatively close shape or whatever, you could prove that there is a single local minima, or is it what you think? Or
So
NPR, in practice it's not NPR.
Yeah, sure. So first of all, I admit I don't completely see the full connection between this and optimal transport, right? I mean, the equations are very simple. Yes, which is optimal transport, right?
It's quadratic optimal.
Yes, of course. It's optimal transport on these pairs of points, right?
This optimal transport is the linearization of
Sure. No, but again, you can think of it as optimal transport on these product measures, right? And product basically couple pairs of points, right? So it's exactly the same, but it's a much more complicated problem. And I think we can probably easily show that what we are doing here is a lower bound on the spectral formulation that Facundo had, I don't know, 10 years back, something like that. But again, saying something more intelligent.
The question is you have an NPR problem, so in practice it should not work, and in practice it works.
Yes.
The Gromov-Wasserstein, when you write it, it's totally useless, it's NPR, nobody should use it. But in practice it works. So
Yes.
it's something that is mysterious to me. And it seems probably the problem we are considering, they are somehow maybe friendly enough that Gromov-Wasserstein or the spectral methods are just working very nicely. So I think this is really very strong.
Exactly. I'm also very surprised why it works. So we probably all these results basically on the computation on the combinatorial complexity of quadratic assignment problems, they don't take into account any geometry of the problem. So I don't have the tools sufficiently delicate to analyze this. We did some work on graph isomorphism, so you can show that in certain cases, under certain assumptions, for example, on the spectrum of the graph, you can give a very simple solution to the graph isomorphism problem. So there are some friendly graphs, but I think here the problem is more complex. Yes, please.
If I understand correctly, you're searching over the space of all permutations, but you have obviously some local topology, otherwise you couldn't do diffusion. So would you not want to constrain, you don't really want all permutations, you want something like piecewise monotonic or piecewise diffuse, whatever the discrete analog of piecewise diffeomorphic is.
I agree. So ideally, I would like to write everything here in the continuous domain and then discretize it. What we are doing, we are first discretizing and then looking for discrete bijection, which is ugly. For example, we need the same number of vertices on x and y, and
why would you do this? I mean, why don't you solve for a transportation problem with Kantor-Rovich coupling instead of the bijection?
Yeah, exactly. We should do it. We should do it. So we were thinking exactly along these lines. I think in these cases the Kantor-Rovich problem is well defined. So we should do it this way. It was just we just had easy access to a good code of the auction algorithm that worked very well. But I agree. This is probably the ugliest thing that I can complain about. We should do it the right way, starting from the continuous formulation.
With the surfaces you're dealing with, have you looked into the connection with conformal mapping or quasi-conformal mapping? I mean, you're minimizing you're using the Laplacian. You have. I mean, are you minimizing the harmonic energy somewhere?
Okay. So I don't have an answer. We ask these questions, so we are constantly asking these kind of questions. So maybe you have some insights, some interesting insights. So it looks like.
But other maybe specialists.
But even this example with the torus, right? So
that's special because you're pushing the method outside of
why?
the situation in which there exists a correspondence.
Well, still. So let's say accept this rotation on the long circumference. The solution seems to be unique, right? And maybe you're getting some things like that with conformal maps. I don't know. Basically, it looks like we are minimizing something that looks like conformal energy. So there must be some deep relation. We haven't thought deeply enough about these two to give any definite answer, but it looks like it is very much related to conformal maps. Thanks.